Wallet best practices. As cryptocurrency wallet technology has matured, certain common industry standards have emerged that make wallets broadly interoperable, easy to use, secure, and flexible. These standards also allow wallets to derive keys for multiple different cryptocurrencies, all from a single mnemonic. These common standards are 1. Mnemonic code words based on BIP39. 2. HD wallets based on BIP32. 3. Multi-purpose HD wallet structure based on BIP43. 4. Multi-currency and multi-account wallets based on BIP44. These standards may change or be obsolete by future developments, but for now they form a set of interlocking technologies that have become the de facto wallet standard for most blockchain platforms and their cryptocurrencies. The standards have been adopted by a broad range of software and hardware wallets, making all these wallets interoperable. A user can export a mnemonic generated in one of these wallets and import it to another wallet, recovering all keys and addresses. Some examples of software wallets supporting these standards include Jaxx, MetaMask, MyCrypto, and MyEtherWallet. Examples of hardware wallets supporting these standards include KeepKey, Ledger, and Trezor. The following sections examine each of these technologies in detail. Tip: if you're implementing an Ethereum wallet, it should be built as an HD wallet, with a seed encoded as a mnemonic code for backup, following the BIP 32, 39, 43, and 44 standards, as described in the following sections. Mnemonic code words, BIP 39. Mnemonic code words are word sequences that encode a random number used as a seed to derive a deterministic wallet. The sequence of words is sufficient to recreate the seed, and from there recreate the wallet and all the derived keys. A wallet application that implements deterministic wallets with mnemonic words will show the user a sequence of 12 or 24 words when first creating a wallet. That sequence of words is the wallet backup, and can be used to recover and recreate all the keys in the same or any compatible wallet application. As we explained earlier, mnemonic word lists make it easier for users to back up wallets because they are easy to read and correctly transcribe. Note: mnemonic words are often confused with Brain wallets. They are not the same. The primary difference is that a Brain wallet consists of words chosen by the user, whereas mnemonic words are created randomly by the wallet and presented to the user. This important difference makes mnemonic word much more secure, because humans are very poor sources of randomness. Perhaps more importantly, using the term brain wallet suggests that the words have to be memorized, which is a terrible idea and a recipe for not having your backup when you need it. Mnemonic codes are defined in BIP 39. Note that BIP 39 is one implementation of a mnemonic code standard. There is a different standard, with a different set of words, used by the Electrum Bitcoin wallet and predating BIP 39. BIP 39 was proposed by the company behind the Trezor hardware wallet, and is incompatible with Electrum's implementation. However, BIP 39 has now achieved broad industry support across dozens of interoperable implementations, and should be considered the de facto industry standard. Furthermore, BIP 39 can be used to produce multi-currency wallets supporting Ethereum, whereas Electrum seeds cannot. BIP 39 defines the creation of a mnemonic code and seed, which we describe here in 9 steps. For clarity, the process is split into 2 parts. Step 1 through 6 are shown in the Generating Mnemonic Words section, and steps 7 through 9 are shown in the From Mnemonic to Seed section. Generating mnemonic words. Mnemonic words are generated automatically by the wallet using the standardized process defined in BIP 39. The wallet starts from a source of entropy, adds a checksum, and then maps the entropy to a word list. 1. Create a cryptographically random sequence S of 128 to 256 bits. 2. Create a checksum of S by taking the first length of S divided by 32 bits of the SHA-256 hash of S. 3. Add the checksum to the end of the random sequence S. 4. Divide the sequence and checksum concatenation into sections of 11 bits. 5. Map each 11-bit value to a word from the predefined dictionary of 2048 words. 6. Create the mnemonic code from the sequence of words, maintaining the order. The Generating Entropy and Encoding as Mnemonic Words section shows how entropy is used to generate mnemonic words. The entropy and word length table shows the relationship between the size of the entropy data and the length of mnemonic codes in words. Entropy, 128 bits. Checksum, 4 bits. Entropy plus checksum, 132 bits. Mnemonic length, 12 words. From mnemonic to seed. The mnemonic words represent entropy with a length of 128 to 256 bits. The entropy is then used to derive a longer, 512-bit seed through the use of the key stretching function, PBKDF2. The seed produced is used to build a deterministic wallet and derive its keys. The key stretching function takes two parameters, the mnemonic and the salt. The purpose of a salt in a key stretching function is to make it difficult to build a lookup table enabling a brute force attack. In the BIP39 standard, the salt has another purpose. It allows the introduction of a passphrase that serves as an additional security factor protecting the seed, as we will describe in more detail in the optional passphrase in BIP39 section. The process described in step 7 through 9 continues from the process described in the previous section. 7. The first parameter to the PBKDF2 key stretching function is the mnemonic produced in step 6. 8. The second parameter to the PBKDF2 key stretching function is a salt. The salt is composed of the string constant mnemonic concatenated with an optional user-supplied passphrase. 9. PBKDF2 stretches the mnemonic and salt parameters using 2048 rounds of hashing with the HMAC SHA-512 algorithm, producing a 512-bit value as its final output. That 512-bit value is the seed. Note: the key stretching function, with its 2048 rounds of hashing, is a somewhat effective protection against brute force attacks against the mnemonic or the passphrase. It makes it costly in computation to try more than a few dozen passphrase and mnemonic combinations, while the number of possible derived seeds is vast, 2 to the 512 power, or about 10 to the 154th power, far bigger than the number of atoms in the visible universe, about 10 to the 80th power. The following table shows some examples of mnemonic codes and the seed they produce. Entropy input, 128 bits, 0C.1A. Mnemonic, 12 words. Army, van, defense, make, crunch. Passphrase, none. Seed, 512 bits, 5B56, 570. Optional passphrase in BIP39. The BIP39 standard allows the use of an optional passphrase in the derivation of the seed. If no passphrase is used, the mnemonic is stretched with a salt consisting of the constant string mnemonic, producing a specific 512-bit seed from any given mnemonic. If a passphrase is used, the stretching function produces a different seed from the same mnemonic. In fact, given a single mnemonic, every possible passphrase leads to a different seed. Essentially, there is no wrong passphrase. All passphrases are valid and they all lead to different seeds, forming a vast set of possible uninitialized wallets. The set of possible wallets is so large, 2 to the 512 power, that there is no practical possibility of brute forcing or accidentally guessing one that is in use, as long as the passphrase has sufficient complexity in length. Tip: There are no wrong passphrases in BIP39. Every passphrase leads to some wallet, which unless previously used will be empty. The optional passphrase creates two important features. One, a second factor, sometimes memorized, that makes a mnemonic useless on its own, protecting mnemonic backups from compromise by a thief. Two, a form of plausible deniability or duress wallet, where a chosen passphrase leads to a wallet with a small amount of funds, used to distract an attacker from the real wallet that contains the majority of funds. However, it is important to note that the use of a passphrase also introduces the risk of loss. 1. If the wallet owner is incapacitated or dead and no one else knows the passphrase, the seed is useless, and all the funds stored in the wallet are lost forever. 2. Conversely, if the owner backs up the passphrase in the same place as the seed, it defeats the purpose of a second factor. While passphrases are very useful, they should only be used in combination with a carefully planned process for backup and recovery, considering the possibility of heirs surviving the owner being able to recover the cryptocurrency.